Bienvenidos, Hushamdi, and welcome to this Hut8 Networking Techtorial. In this Techtorial, we're going to be taking a look at how Python can make your life with EIGRP and the composite metric calculation much easier. I'm actually teaching a CCNP route course right now at the University of Maryland University College, and we just finished covering EIGRP. And one of the more complicated topics when you talk about EIGRP is that composite metric calculation. Now, when we've got our default K values, what happens is it really comes down to bandwidth and delay. And so we're going to take 10 to the 7 divided by the bandwidth, and then we're going to go ahead and take the delay and divide it by 10, and those are the numbers we're going to be using to add together to then multiply by 256. Now, where those values come from, how we can manipulate those values, and why we use 256 to multiply bandwidth plus delay at the very end of the equation, we're all going to cover here. In fact, I'm going to give you the Python scripts for both Python 2 and Python 3. The last time I did this tutorial, which seems like ages ago, it was so long ago that I had done it up in Python 2. So I've updated it so we can see what it looks like in Python 3, and I'm going to make it a little more Pythonic from the perspective that we can consolidate some of the code in that file. So let's go ahead and take a look at the setup that we're going to be working with. We've got 3 routers connected together. We've got router 7 directly connected with router 8 via fast Ethernet 00.78. And then we have router 8 and router 9 connected together with a point-to-point serial link, serial 000. I've placed the bandwidth in kilobits per second because that's the value that we're going to be using with that EIGRP composite metric calculation. So we can see the speed of the link here between 7 and 8, between 8 and 9, and we're going to be going to the loopback 0 address of router 9, and there is a speed associated with that loopback address from an EIGRP perspective, and there is a delay, right? Even though it's a software address, it's a logical address, not a physical address. We still need to take into account that there will be delay and a speed associated with that loopback address. So here are the values that we're going to be working with. Now, we're also going to see how the show IP EIGRP topology command can help us out here. So let's jump onto the command line and let's see how we would take a look at these different values. So if I'm on router 7, one of the key things to remember is we're looking at the values on the outgoing interfaces. So if I said show interface fast Ethernet 00.78, this is where we would see the delay in microseconds. That's what that little U means. Now, one of the tricky things with EIGRP is when we go to set that value or manipulate that value for layer 3 traffic engineering purposes, we're going to be entering in the value in tens of microseconds. So if I went to the interface, I would say delay 10, and that would result in that being the delay in microseconds. So if I said delay 100, it would be 1,000 microseconds. Delay 10 gives us 100 microseconds. And then you can see here, it's a fast Ethernet interface, which is 100 megabits per second, but in kilobits per second, it's 100,000. So we want to talk about where the values are that we are interested in. And so let me highlight those as green. So it's going to be that outgoing interface right there, right? The one that we just looked at on router 7. So that is where we're going to be getting the values from because we're calculating what it's going to cost to reach the loopback over here on the right. Now, a common mistake that a lot of learners make is they see that I need to get the delay and bandwidth, and again, it's the cumulative delay, but it's the slowest bandwidth along the path, and so they'll look at every interface. So they may be looking at this interface right here as well, but if we're talking about the 9999 over here behind router 9, and we're going from left to right, it's only the outgoing interfaces. So it would not be this interface right here, and it won't be that interface right there. Those are the inbound interfaces. So let's go ahead and clear that out. So I've got the values for this interface, I've got the values for that interface right there, and we have the value for this interface right here. And they're on the screen. So now what typically happens is you have to do this calculation manually. So in other words, I would find the slowest bandwidth along the link, and in this case we can see that that's going to be 1.544 kilobits per second. Here we've got 8 million kilobits per second, and over here we've got 100,000. So no question that 1.544, it's 1.544 megabits per second, but it's 1,544 kilobits per second. So no question that that is our slowest link. So I would take 10 to the 7 and divide it by 1.544. And that value is going to give me the bandwidth value that I'm going to be using in my equation. Now, I take the cumulative delay, which means I'm going to be adding the delay up of the outgoing interfaces from my source to the destination. Well, we can see here that the delay on the fast Ethernet 00.78 is going to be 100 microseconds. The delay over here on the serial link, which is much slower, is going to be 20,000 microseconds. And then finally, the delay for that loopback interface, which we have to take into account, is 5,000 milliseconds. And so what we would have is we would have 25,100 for our delay value. And we'll say equals, and I'll just put DLY here. Now, what I would do is I would take the result of this equation, and we've already got the result here, and we're going to add those together. And it's after we add those together that we multiply by 256. And now you may be saying, well, why are you multiplying by 256? Well, remember, EIGRP, the Enhanced Interior Gateway Routing Protocol, is an enhanced version of EIGRP, which was the original Cisco Distance Vector Routing Protocol Interior Gateway Routing Protocol. EIGRP was based on 24-bit metrics. So EIGRP was 24-bit. EIGRP, to give you a little more resolution and a little more granularity, uses, and this is the classic EIGRP that we're talking about, not named mode, which is 64-bit, but classic mode, I'll just put CLS for classic mode here, uses 32-bit values. And so the difference when we're talking about powers of 2 here is going to work out to be 256, because you can see the difference is 8, so 2 to the 8, right? Because we've got a difference of 8 here. If I was to subtract 24 from 32, so we go by powers of 2, 2 to the 8 is 256. Right? And so that's where that value comes into play. And again, it was to provide better resolution, more granularity when we're looking at the EIGRP metrics as opposed to the EIGRP metrics. And remember, EIGRP is deprecated. It's not a routing protocol that's being used anymore. And so that gives us a good foundation. Now, again, when you look at the equation for the EIGRP composite metric, when we're talking about classic mode, you might think to yourself, I need a degree in math to figure this out. But again, remember, the only composite metric values used by default, and really the only composite metric values that you should be using, are bandwidth and delay. And so again, we do 10 to the 7th divided by the lowest bandwidth on the outgoing interfaces along the path from the source to the destination. And then we add up the delay. We take the cumulative delay, and you can simply type show interface on the outgoing interface along the path, and you can figure all of that out. So we take the bandwidth, add it to the delay, multiply by 256. Now, you can do this by hand. There's nothing wrong, but when you get in a really large environment where you've got a lot of routers involved, this can become quite time consuming. Here, you can see that we're simply looking at 3 different interfaces. In fact, if I was to shift back over here to the topology, if I started on router 7, we've already done the show interface on fast Ethernet 0078. I would move over to router 8 and I could say show interface serial 000, and there are my bandwidth and delay values. And then I would come over to router 9 and I can say show interface loopback 0, which is the 9999, and there is my bandwidth and my delay. So for 3 routers, not that big of a deal. But when we're talking about 30 routers, this is not something you're going to want to do. But Donnie Savage, Don Slice, and the crew have provided you with a beautiful shortcut to get everything you need already presented to you. And that is the Show IP EIGRP Topology. And we put in the destination network that we're interested in getting the lowest bandwidth along the path for, as well as the cumulative delay. So in other words, I say show IP EIGRP topology 9999/32. I do that on the router from which I want to calculate these values. And that command is going to give me auto-magically the minimum bandwidth along the path in kilobits per second, and then it's going to give me the total delay in microseconds. So in other words, I'm being given all the values that I need right here with a single command. I don't need to go interface by interface, router by router, collecting these things up, documenting these things. It's a single simple command. Now, again, we still have the challenge here that I'm going to have to figure this, I'm going to have to work this out by hand. I'm going to have to divide 10 to the 7 by 1544, and then I'm going to have to divide the delay 25,100 by 10, which is easy. We can just drop that last 0, but maybe it's not a 0, right? Maybe it gets a little more complicated. So in other words, wouldn't it be great if we had a script that we could pump these values into 1544 and 25,100 and then have that script output what the composite metric value is going to be. And there's our metric right there. That's our computed distance. And it's 2,300,416. So let's first go ahead and take a look. I've got 2 scripts here, and let's take a look at EIGRP2.py. In other words, it's a Python script written in Python 2 in order to calculate the composite metric. Now, the first thing you're going to notice is it's not very Pythonic, and that's if you're familiar with Python. But we're going to go ahead and clean this up when we look at our Python 3 example to make it a little less complicated, or I shouldn't say a little less complicated, but make it fewer lines in the code and kind of combine things. But this breaks things out so that you can see what's going on in a nice, clear fashion if you're not familiar with the Python programming language. So with Python 2, we have to say raw input. I'm prompting the user here, give me the minimum bandwidth in kilobits per second. So then I convert whatever the user enters in, because by default, the raw input command is going to return a string. Well, I can't do mathematical operations on a string. I need an integer. So I convert whatever the user enters in into an integer. Now, we could combine that with the first command, but hang with me, we're going to get there in a second. Now I've got the bandwidth here. There's 10 to the 7. You can see 1, 2, 3, 4, 5, 6, 7. So there's 10 to the 7 divided by the bandwidth. In our case, it would be 1544. And then it's going to tell you, after dividing 10 to the 7 by the bandwidth, that's the value that we're going to get for the bandwidth, and I have to convert it back to a string here because I'm doing concatenation of this output with the print function, or the print statement. And then we've got our delay, right? Again, we prompt the user for the delay. I convert what the user enters in, which is going to be, by default, interpreted as a string in Python. I change it to an integer because we're going to then divide the delay by 10. Again, we go from the microseconds value and we take it back to tens of microseconds. And then we get our composite metric value, which is nothing more than the bandwidth plus the delay times 256. right? So it's not really that complicated. Again, that formula that you see for the EIGRP composite metric with classic mode is extremely complicated, but when we hammer it out and really trim down what is being used and which values I need to have and how I get those values, it's very, very straightforward. And so then I'm going to simply print out, and again, converting what is going to return an integer to a string so that I can concatenate it here. I just simply say your EIGRP classic mode metric will be, and then we get the values. Well, let's go ahead and run this through and see what we get here. So I'll say /EIGRP2 .py. So the minimum bandwidth along the path in kilobits per second we know is 1,544. And then that gives me the bandwidth value, 6,476. Remember, we are doing integer division here, right? Not floating point division. EIGRP doesn't deal with decimal places. It uses floor division. Now the cumulative delay was 25,100. Remember, we had to add the delay of every outgoing interface from the start of our path, right? From the origination, the source, to the destination. And we get our classic mode metric of 2,300,416. Well, let's see. Is that what we've got? 2,300,416. It absolutely is. So let me go ahead and show you that script one more time, EIGRP2.py. And so there it is. Again, not very Pythonic. There's a lot of things that we could consolidate here that we haven't done. But we're going to be doing that when we take a look at how to do it with Python 3. And really, you should be doing all of your programming going forward. Unless you're working with some legacy code, you should be using Python 3. So let's take a look at what the EIGRP 3.py file looks like. And you're going to notice that it's almost identical with the exception of two very small differences here. Now, one of the differences is in Python 3, in order to get that floor, that integer division, I have to have 2 forward slashes instead of just 1. If I just put 1, we end up with decimals at the end of the division. So we need to use 2 forward slashes here. Now, I've pulled in something to clear the screen to make it a little nicer to look at. And the second difference is we no longer say raw input, you just simply say input. So those are our major differences. We say input in Python 3 instead of raw input, and then in order to get integer division, we simply use 2 forward slashes instead of 1. And those are really our only differences in this script. All right, so let me go ahead and clear that. And let's run this real briefly, and then I'm going to go ahead and tweak it, and we're going to consolidate things down to make it a little bit more Pythonic. So if I was to say /EIGRP3.py, the minimum bandwidth, you can see the screen has been cleared, right? I say 1544. There's that same value we saw, and then 25,100. And there we go, 2,300,416. And so the Python 2 script works and the Python 3 script works, but now let's dig in. And in fact, I'll make a copy of it here. So we'll say copy EIGRP3.py, and we'll copy it to EIGRP3.1.py. And so let's pull up EIGRP3.1.py. So I keep making this comment, it's not very Pythonic. And the reason it's not very Pythonic is because I put the code here sort of in storytelling mode, or almost a pseudocode mode, where I would say, all right, as a learner, you enter the bandwidth, right? And then we need to convert it to an integer. And now that we have it in integer format, we take 10 to the 7 and we divide it by that bandwidth value as an integer. And we're going to get an integer back, right? Now, do we need to do all that? Well, in Python, we don't, because I could even, I could come here and I could say int, and I could place this entire input statement and convert it automagically to an integer. And so I don't need that line anymore. Now, what if I was to go ahead and say 10 to the 7, 2, 3, 4, 5, 6, 7, and do this? Would that work? Well, let's take a look and see what's going to happen when we do that. So if I was to save this and say /EIGRP3.1.py, I'm going to enter the bandwidth 1544, and you can see it does work. So 25100, I could even consolidate that line down to a single line. And so that's going to make it look more Pythonic. Again, definitely more complicated to look at that from a beginner perspective, but this is how we could trim that code down to a single line. And if I can do it there, right, if I could take 10 to the 7 and divide it by everything I get back, why could I not do the same thing here? So I do the integer, we'll go to the end of the line, whoops, go to the end of the line. So now the question becomes, I need to take that delay value and divide by 10. So before I was taking 10 to the 7 and dividing it by everything I got back. Here I need to divide everything. So what is that going to look like? Is this going to work? Well, let's come back and take a look here. We'll drop all the way down to the, to the beginning of this line. I'm going to comment that out because we don't need that. And let's run it and see if that does what we think it's going to do. So I'll say 1544, and there's my value, and I'll say 25,100. And take a look at that. So we can trim both of these Python statements down to a single line. And then I've got my composite metric, which is the bandwidth plus the delay times 256. And then I simply print that value out. Your EIGRP classic mode metric will be, and then I concatenate and convert to a string the composite metric value, which is an integer at this time. And that is an easy way to trim down your Python 3. So, and you could do the same in Python 2, but I'm focused on Python 3 here. And that's how we can trim it down to get us that EIGRP composite metric value all worked out in a minimal number of lines. All right, well, I'm really hoping that you've enjoyed this tutorial. I'm going to be trying to weave Python into the conversation because this is definitely a language, if you're in the networking space, that you're going to want to start learning about and becoming familiar with. So you've got the Python 2 EIGRP file that you can replicate. You've got the Python 3 EIGRP file that you can replicate. Neither of those are very Pythonic. And then we did 3.1 where we really consolidated things down and came out with a very nice version in Python 3 to calculate, compute, and print to the screen the EIGRP composite metric. All right, thanks so much for watching. Enjoy the rest of your weekend, and I hope you enjoyed this video.